Howdy folks, my name is Arul Verma, and this week I'll be going over data types and functions in the lecture for students from the honors. So our goals for today are to talk about compound data types. If you remember last week, we talked about scalar data types, particularly our integers, our floating points, our booleans, and our characters. And this week we'll be going over arrays and tuples. We'll also be going over functions and vectors. So again, let's talk a little bit more about what data types are. If you were paying attention last week, you'll remember that data types are the methods by which we tell the compiler what type of data to store. They're built into the compiler, so the users can access these data types with predetermined keywords. There are two types of predetermined data types, scalars and content data types. Scalars, as I mentioned earlier, are your integers, your floating points, your booleans, and characters. They store a single value, and they are generally just a single value. You cannot store multiple pieces of data, and they're not able to store wide types of data. You can only store a singular type of data in those predetermined types. The contrast of that is the compound data types, which are our tuples and arrays. So let's talk a little bit more about those. First, let's look at tuples. Tuples are fixed length ways of returning multiple pieces of data. They can store multiple values of different types, and you don't need to declare those types. So let's take a look at some code to see kind of how that works. So here we have our first declaration of our tuple. We have let x colon I32 F64 U8. So we can see our type declaration is there. And then we have the actual value, 500, 6.4, and 1. But if we look at a second declaration of a tuple, we can see that we omitted the type declaration entirely, and we just gave our tuple. This is also an acceptable type of code. So you don't need to declare, you can implicitly declare your types of your tuple, but generally you do want to be declaring those types because your tuples are immutable. You cannot change them. So you want to make sure that the value you're storing and the length of that data is correct, because that can cause issues in memory. Tuples are zero indexed. So if you want to access the data in your tuple, you have to start from counting from zero. So this would be the 0th index, the first index, and the second index. And you would access that data using the dot notation. So x.0 would give us access to 500, x.1 would give us access to 6.4, and x.2 would give us access to 1. Empty tuples are called units, and they're generally the default return value for functions. So if you don't specify a return value, you'd be just returning an empty tuple. And the value and type for a unit is just the parentheses with nothing inside. So if you were to return a function, have a function return nothing, and see the type of that, you just get parentheses. One thing I forgot to mention is that other than dot notation, you can also access elements in your tuple using the format seen in the bottom right, where you say let x comma y comma z equals 2. And you can access individual elements by using x comma y comma z as those elements. So x would be assigned to 500, y to 6.4, and z to 1. But they would, of course, also be immutable. And they're just ways to access that data as opposed to the indexing from the dot notation. Arrays are the other way of storing data, the other compound data type. And something that's very unique to Rust arrays is that unlike other languages, arrays are fixed length. You cannot change the length of your arrays. So if you come from Python or C++, this would be kind of different from your experience because you can't actually play with your arrays as well as you can in other languages. One thing that is very streamlined across all languages is that arrays must store the same type value. So you must be storing all integers, all booleans, all characters, and implicit declarations for your type are allowed. So you can see what I mean by looking at the right. This is completely valid code where we have an array A equal to square brackets 1, 2, 3, 4, 5. And this would just be creating an array with these 5 values. Arrays are mutable. You do need to use the mute keyword, but you can change the values inside them, unlike a tuple where even the mute keyword will not allow you to change those values. And the way you would access and change elements is by zero indexing. So you'd be using these square brackets to index, starting from the 0 in the first place, and then first, second, third, fourth, and this would be 0th. And if you use an invalid index, you'd throw a trace error and panic your code. So it's important to be aware of the counting your index correctly. So I talked about implicit declarations and explicit declarations for arrays. You can do some fun things when you're declaring your type of your array. And you can see it on the right here. You can see that this code declaration looks a little non-standard, and that's because it is. Rust has a unique way of declaring its types for its arrays, and that is by using a square bracket, the type, and then the length of your array. So it's kind of a different way of writing your array and declaring it, as opposed to other languages. And it's something that like a non-Rust user would have a hard time reading. So it's a good way to make your code a little bit more complex, a little bit more mystique, and do it in a way that doesn't functionally change your code. Another good thing to know is how you can declare arrays of any length with all the same value. So if you look at the bottom right, we have this piece of code, let a equals square brackets 3, semicolon 5. And what this does is it has an array of length 5 with all its values equal to 3. And so you can see we have the same piece of code, just written slightly differently. Let a equals square brackets 3, comma 3, comma 3, comma 3, comma 3. And these two pieces of code are interchangeable. They do the same thing. They both create the exact same array, stored in different places in memory, of course, but the array stores the exact same values. So this could save you a lot of typing when you're trying to create an array of an arbitrary size, an arbitrarily large size, all with the same piece of data. So it can make life a lot easier. So it's a good way to know how to declare your arrays of indeterminate length of the same value, and it can be useful in the future. So now let's talk about functions. So functions in other languages can be declared in multiple ways. Generally, when you're declaring your function, you have it typed in a certain format. In Rust, that format convention is called snake case. And that means all of your words are lowercase, and you use underscore to separate distinct words. And this is something that would be very familiar to you if you've programmed in Rust before, because Rust also uses snake case, or sorry, not Rust, Python, because Python also uses snake case, just like Rust. And other languages like C++ generally use camel case as their standard. And this isn't something that we enforce or require, but it is kind of a nice quality of life feature, and it is good to know because it is the standard in programming in Rust. Now, another thing about programming functions in Rust is that the order of declarations of your functions does not matter. If you've programmed in C++ before, and you look at the code in the bottom right, you'll think that it looks a little odd. And that's because the function print label measurement is beneath our main. And that's kind of non-standard because generally when you write functions in C++, like this, you'll cause an error because the function declaration is after the function call. And what I mean by that is that we call print label measurements with some parameters before we declare our print label measurement function itself. And the reason for that, and of course, if you don't follow this, that's totally fine. I just want to give you kind of an insight of how functions and their memory work and why it causes an error to and not in Rust. But this is something that will be covered more extensively in other classes, and it isn't something you need to understand for this lecture. But essentially what I'm trying to say is that in C++, what the code does is it goes from top to bottom, and it creates memory instruction for each one of those lines of code you've written. So this line of code for print label measurements, 5, H, gets a piece of memory that has an instruction saying, do this. But the code doesn't know what print label measurement is because it hasn't reached this point where you declare a print label measurement to do something. So it's not entirely sure. It reads this line of code and isn't entirely sure what to do with that data of 5 and H. But in Rust, what the compiler does is it goes through the entire code and it makes instruction memory for your functions first. So it makes instruction memory for your main, then instruction memory for your print label measurement or whatever other functions you've declared. And then it goes through and makes instruction memory for all of your variables. So it would make an instruction memory. So if I made like an int x, it would make instruction memory for that. And then finally, it'll go through and make instruction memory for all of the actions we do in our code. So printing our label measurements or whatever else functions we do, values we do inside of our code or changes we do inside of our code, then it will make instruction memory for that. So when the compiler is going through and running this code, it doesn't have a conflict because it knows exactly where to send its memory because it's already created a print label measurement function in its memory itself. Of course, this is all well out of the scope of this class and what you need to know for this lecture, but it's just, I thought it would be something cool to share and explain how memory works and how it's different in C++ versus Rust. So back to more about functions. Functions have a keyword fn, which indicates that you're creating a function and you're declaring it. And then you put the name in snake case. Then you put your parentheses. I'll go over more about what those parentheses do in a minute. And then you put your curly braces. The curly braces indicate your function body. And whatever you want to do when that function is called, you put inside those curly braces. So now let's talk about parameters. I briefly mentioned it with the parentheses, but let's get back into it. Whenever you want to pass values into a function, you pass them as a parameter. Parameters go inside these parentheses, and they must have a type declaration. So you can see an example with print label measurements. Inside these parentheses, we're passing two values, value and unit label. both of which have a type declaration. You cannot implicit type here, and that will cause an error. And parameters are by default passed by value, and they are immutable, meaning that if they are edited, the changes are not reflected outside the function. So let's take a look at like what that means and how that's applied. So you can see I have some code here. We have let mute x equals to 10 and change x, where change x will increment x by 10. And then we print x. So if we were to run this code and comment out this line, you would think that we'd be printing 20. But in reality, we just print 10. And then if we uncomment this line, you'd be thinking we'd be printing 2020. But we'd actually be printing 2010. So why is that? The reason for that is that the way the compiler works in Rust and many other languages is that when you're passing by a value, or just passing a value into your function in general, it takes that value that you're passing and creates a clone of it. And that clone is sent to the function to use as it sees fit. So we have two values of x is equal to 10, even though we don't know it. And one of those values is sent to change. And change will increment that value that it's stored, that clone, by 10. And that's why when we print it, we get 20. But once we go back from this function change back into main, that clone goes out of scope. It's destroyed and no longer exists. So when we print x, we get 10 because that value no longer stores 20, it just stores 10. Now, if you want to take a sneak peek at how code is written where we want to change that value, in other words, pass by reference, so that the value of x changes without making a clone of it, we can use this code. It looks very similar, but if we would run this, we would get 20 instead of 10 in our output. And the few things that you need to know about how references work will be gone over in a later lecture. You don't need to understand the scope of this lecture, but all you need to know is how references are done using the and symbol, and they're also done using the asterisk symbol. So those nuances are something that are well out of the scope of this lecture, but this is kind of just to give you a sneak peek of how you can potentially write code that would pass a value into your reference, or pass a parameter by reference, and then change that value so that it's reflected outside that function. So if you're paying close attention to that code I showed you earlier, you'll notice that we use the keywords mute, the and symbol, and the star are all part of our parameter type. So when we're passing a parameter, we put the and symbol and the mute as part of the type, and then we followed it up by like I32. And that's because when the compiler is looking at our code, it needs to know exactly what type is being passed into our function so it can assess those values correctly and know exactly how it can use them, whether it can change them, and what changing them would have as an implication. So it's important to pass mute the and symbol and the star when you use them so that your function knows exactly what to do with that data. Functions can also return data after their call. So an example of this is on the bottom right, where we have function 5 returning the value of 5. And the way you return a value is with the arrow key, which is just the dash and the greater than symbol. Afterwards, you have to specify a return type. You can only specify a single return type, and you must specify it. You cannot implicitly specify it. If you want to return multiple values, you have to use a tuple and array because functions cannot return multiple values on their own. Tuples allow you to return multiple values of different types, and arrays allow you to return multiple values of the same type, but both allow you to return multiple pieces of data together in a single function. So now let's talk about the last part of today's lecture, vectors. So we talked a lot about data types and functions earlier, but vectors are not data types that the compiler recognizes. Vectors are classes, and they must be declared explicitly. They are in a library that is separate from the normal library that Rust uses, and this library is included in the crate that we provide for the Rust homework, or all the Rust homeworks for this class. But they are not part of the immediate Rust library that are like data types are a part of. And because of that, you need to recognize that they're different. They are classes and they are not data types. And that means that declaring them is a little different than declaring a data type. So let's take a look at our bottom left, where we have some code where we declare vectors. So vectors can only store a single type, and you'll notice that immediately when we have our first declaration of a vector. We declare our vector using vec, and then we specify the type it can store. And then we say equals vec : new. This is the first way we can create a vector where we specify the type of value it's storing, and we give it all the single type. Vectors can also be declared using the vec ! Macro. And here we don't have to declare a type, but that's because we already give the values to store inside our vector, and it implicitly decides the type that we're storing inside. So if you want to take control of what type you're storing, you have to declare it using the first method, but then you'll have to push values manually because there's no way to store those values immediately. But if you don't want to declare the type, you can use the macro. Vectors do have a variable length, and they are mutable. Unlike tuples, where if you use the mute keyword, you can't change them, vectors can be changed if you use the mute keyword. And you can change the length if it's mutable by using the dot push function, something we'll go over more in the next slide. One word of learning about using the macro versus using the declaration type is that they are not interchangeable. If you have a function that takes a vector of the macro declaration and you try and pass a normal declaration in, you'll have an error because those two types are not the same. And the same applies if you have a function that takes the normal vector type and you pass a macro, that'll cause an error because those two types are not the same. If you want to use them interchangeably, you need to use a transformation function built into Rust. And the compiler will tell you what the transformation function is. So it's very easy to change between the two, but they are not the same. And it's important to recognize that fact. You can access data inside your vector using the square brackets notation. And that's something let's go over in the next slide, where we can see we access that element in the bottom right. We have our vector v, and we declare it using the macro 1, 2, 3, 4, 5. And we access the third using v square brackets 2. So because the vector is 0 index, we go 0, 1, 2, and we see third stores 3. So it's important to realize that it's 0 index, and you can access with elements using the square bracket notation if you want to play with your vectors and access individual pieces of data from them. If you want to increment your vector or increase values, add values, or change the length of your vector, you use the dot push function, which you can see illustrated in the bottom left. We have our immutable vector v declared with vec new, and then we push values in using 5, 6, 7. And if we were to print v here, we would see our vector have values 5, 6, and 7. If you want to access elements earlier, as I said, you can use the square brackets, or you can use the dot get function, which is a built-in function for vectors. However, the dot get function will return an option. So it's something that's out of the scope of this class at the moment. We haven't taught you options, but we will in future lectures. And eventually you'll understand how to use dot get. But for now, it would be easier if you use the square brackets, just because that's the best way to access individual elements without having to learn options and results. And before we go into some sample code using some vectors, I want to show you the bottom right example where we iterate through a vector declared using the vector macro. So for loops can also be enhanced, as I went over last lecture. You can say for I in v, and this will just go through all the elements in our vector v, and you can print them out individually. So that's kind of how you'd iterate through the elements. And another way to do it would be, of course, iterate through the length of your vector and access through v square brackets and then the index. So now let's take a look at a little piece of code on vectors themselves and how we can kind of play with them and change the values. So if we were to run this code, we have a mutable vector declared using the vector macro. And when we first print our value, we print our value in 1, we get 0, 1, which would give us 2. And then we say vector 1 is equal to 5. So we change the value stored in 1. And if we print it a second time, we'll get 5, which is now the new value stored in the index 1 after we changed it using the square brackets notation. So this is kind of just to show you how vectors work, how you can change them, and help you guys get familiar. So I'd highly advise taking this code and building a more complex case out of it and playing around with it to understand how vectors work and what the limitations of vectors are. So before we end for today, I just want to give you some quick reminders. We do have extra 0 credit practice problems that are open on Verilor. I'd highly advise you do them just to get an idea of how Rust works, how Rust syntax works. And they are relatively basic problems, but if you do need help, feel free to reach out to us in the Discord on kind of how to code those problems and how to use Rust to solve those problems. Other things to know is that homework 1 will be releasing this week. So keep your eye out for that and make sure to get ahead when it does go out, as we do find that people who tend to start early also tend to do better in this class. So it's very important that you hop on that as early as possible. As always, we do have lectures in the Rust documents if you want to, we have chapters in the Rust documents if you want to follow along with our lectures. The content data types are all in chapter 2. Functions will be in the end of chapter 2. And if you want to go over vectors, you can go to chapter 8, where they'll give you a more in-depth explanation of the same things we went over. And we will eventually cover the entire chapter 8 as we go over borrowing and referencing later. But for now, we only go over the beginning. So yeah, that was everything for today's lecture. Thank you all for watching, and I look forward to seeing you guys next week.